So welcome student. Let us start our lecture today. So this EMA 425 topology, and today we will start learning another very important idea. It's called connectedness. And this is also one of the very important topological property. With the help of that, we can distinguish two topological spaces. Okay, so we'll come later. Okay, so let me start with the definition. So as usual, so we have some x and tau x topological spaces. Okay, space, and so then let us define something called separation. So separation of x is a pair. So maybe like write down UV of disjoint non-empty, both non-empty. Okay, open subsets. It's a pair, so I don't need subset. Pair means, yeah, no problem. Subsets. Okay, set of x with union is full. So U union, the union of V is the full set. Okay, so what does that mean? That means separation means, so the pair of two open sets and they are disjoint and non-empty such that the union is the full set. Okay, then it is called a separation. So this is the definition of separation. And what do you mean by connected space? So a space is called connected if there is no such separation. Okay, so X is said to be connected if there does not exist any separation, does not exist any separation of X. Okay, so then it's called connected, and otherwise it's called disconnected and is called disconnected if there exists a separation. Okay, simple definition. So for example, you just draw the sun. Let me draw some pictures. So examples. Okay, so I will prove in maybe up to some time that real lines is separable, but let me just see in say in a plane, you say open balls. Okay, open ball mean without the boundary. So these are all connected. Okay, so in a real line you can see that kind of intervals. Okay, these are all example of connected space. Okay. Okay, and obviously there are many ways you can define this definition. So let me say one more way. So or you can say theorem or note. What should I say? The following are equivalent. Okay, so this X is connected. Connected means with respect to topology. Maybe I will show later that if you change the topology, then the property may be changed. Okay, so now I'm saying X, I mean X tau. I'm not writing tau always. Okay, and then um, if U subset of X is both open and closed, then either U equal to empty set or U equal to X. There is no other option, and this is obvious that the empty set and full set X, they are both open and closed, right? They have both the property. But in the connector space, we will prove that these are the only two sets having this property. There is no other set that is both open and closed. Okay. Okay. So let me prove it. Proof. Say 1 implies 2. So that means I'm assuming that is connected. That does not give separation. Then we will show that only two such things. Okay, so let X be a connected space and so let me assume that there exists something which is both open and closed. Okay, and then let's see. Okay, and U subset of X is both open and closed. Then obviously X minus U is open also, because U is closed, X minus U is open, and you can write down X equal to U union X minus U, and so this is a separation. Okay, so which is a contradiction, so which is a contradiction. So what does that mean? That means you cannot have something which is non-empty. Okay, and I'm assuming that is non-empty. Obviously U is non-empty subset of this. Okay, if it is empty, then there is nothing to prove. Okay, clear? So this part is obvious, and second part is also simple. It's 2 plus 1. So I'm assuming that whenever something is both open and closed, has to be 5, and then we'll show that we'll say that F is connected. Okay, so on the contrary, if X is not connected or disconnected, then what happens? If F is disconnected, then there exists U and B, the pair, this pair of non-empty, empty, open, non-empty open sets. Okay, so this is non-empty open sets, and also disjoint. Okay, and disjoint. Okay, I should write down disjoint first, but okay, such that what happens is that U union V equal to X. Okay, and hence your V can be written as U minus X minus U, right? And because U is open, so V is closed, and B is also open, so U and V are both open and closed non-empty proper subset of X. Okay, so so again this is a contradiction because I assume that there does not exist any proper subset of S which is both open and closed, right? So this is a contradiction, and hence X is connected. So what does that mean? That means instead of telling openness, you can replace openness. Not openness. Instead of telling that the existence of separation, it is enough to say that there are only two sets are there which are both open and closed simultaneously. These are nothing but the empty set phi and the full set S. Okay, clear? So maybe we can give some more example. So for example, so let me write down my X is real line. Okay, I mean we will prove this is connected. You just assume that. We will prove that this on any ordered set with ordered topology is connected. Okay, for example, the equivalent topology of R is nothing but the ordered topology of R from the usual ordering. So if you choose any proper subset, so let me write down, say 1, 2, union 3, 4. Now you see that this is not connected because this 1, 2 is both open and closed in Y, but not equal to phi or Y, right? It's neither phi nor Y, right? So these are examples that you can easily find out. Okay, now for subspace you can replace the condition open by another property of using limit points. Okay, and this is important because in some cases we will see that in some cases the limit point argument will help us to prove many important theorems. Okay, so let me prove another proposition here. The property maybe proposition. Okay, no problem. So you have is topological space X and the subspace Y. So let Y be a subspace. Okay, and then for subspace we can replace the openness, the property of openness, by another property. So we'll say that a separation of Y, okay, is this pair, say UV of disjoint non-empty sets such that so U does not contain the limit point of Y and vice versa. So how do I write down such that neither of each contains a limit point of the other. So what does that mean? That means U does not contain limit point of X and X does not contain limit point of Y. So this is the property. If we assume, then this is actually equivalent to the open property. that means u and v are both open. Okay. Or rather you can say that yeah, so both open, or you can say that you have a u is both open and both closed. Okay, both are equivalent, we just prove it. Okay. And in this case, if y has no such separation, then we say that y is a connected subspace of the full space. Okay. Okay. So how do you prove that? So the separation, we can replace the separation idea of full space inside the subspace by this idea. So separation means you can replace the openness by this, and this is a proof obviously. So let us prove it. So let me assume that first you have separation, and then I will assume that if you have a separation, then this satisfies the condition which I just assumed, that one they will not contain the limit point of the other set. Okay. Now how to prove it? So let u v be a separation of y. Okay. So what does that mean? That means they are open, disjoint. Okay. And hence u and v both are closed also. Okay. So thus u is both open and closed in y, right? This is we just proved before. Now if we have something which is open and closed, then we can have something called closure, right? Then what will the closure? So the closure of u in y is what? Is nothing but closure, the full closure intersection y itself. This is the closure of u in y, right? That we already proved long back ago. We take the closure inside the full space x, and they take the intersection. That will be the closure. Okay. So now, so this is the closure of u in y, but you know that u is closed, right? So what does that mean? As u is closed in y, what do you have? So you have u equal to u bar u closure intersection y, right? Because the closure of u in y is this, and u is closed, so that has to be equal to this. So that means the limit points are all inside u itself, right? Okay. So this implies u contains all its limit points. Okay. So now yeah, so now the important thing is that what is v? V is disjoint from u, right? But you also one more thing, you know. Okay, so this is the property of u, and then what is the property of v? V is disjoint from u. So you know that u u intersection v is phi, that you already know, because we assume that u v, this is a separation, and if u is equal to u intersection y, then what is the property of v? So this implies v u bar, y bar, and v bar is also phi, right? But v is a subset of y, right? Because v is a separation, so v is a subset of y, and because this intersection is empty, and this implies that u bar intersection v has to be empty, right? Because y and v, intersection of y and v equal to v itself. So you just use the associative property, right? A into b into c equal to a into b into c, like that property. So y intersection v is v, and this has to be equal to phi. So what does that mean? That means the intersection with v with u bar is also phi. So that means the limit points of u are not inside v also. What I am assuming, claiming. Okay. So thus v does not contain any limit point of u, right? And the proof is similar for the other one also. And similarly, if you see, I have started with u, right? U is both open and closed, but b is also both open and closed, and then you can play the game with b also. So similarly b u does not contain any limit point of v. Okay, and that is the proof. What we want to prove, that for the subspace, if separation means, then you can talk about inside the limit points also. Okay, or obviously, see, I mean, you can do it for full space, but for subspace, you know that limit points are points of the main space, right? That's why you require subspace property. Now conversely, let uv be a pair of non-empty disjoint sets such that u union v equal to y, and we will show that both u and v, they are both open and closed. Then that means that this is a separation, right? Okay, so sorry, 1 minute. Both such that these and neither of them, okay, that property I need to assume, right? Neither of them, or whatever them contains a number of contain a limit point of the other. Okay, this is the property I am assuming, and I will show that with the help of this property that uv forms the separation. Separation means that they are both open set. So what does that mean? Both open mean they are both closed also inside y, right? So if I prove that u is both open and closed, I am done. That will implies b is also both open and closed, right? Now if if u and v does not contain each other limit points, so thus what we have, so thus u closure intersection v is empty, because v does not contain limit point of y, and obviously u intersection v closure is also empty. Okay, you understood? So this is the property that both happens. And now once u intersection v is empty and v intersection u is empty, so can you now say that what is the property of a intersection u? So now u intersection y, or rather u by intersection y. So now u by intersection y can be written as u by intersection y means what? It is given that it is v union u, v union u equal to y, right? So this is y. Again, you just use the associative property. So u bar intersection v, and then yeah, so 1 minute. Yeah, so this union U bar I'm missing something. So y equal to v intersection u. So u intersection y is nothing but u intersections b union u, which is nothing but u intersection b union u intersection union u or intersection u and something is missing. 1 minute. Yeah, so I need to prove that u is closed, right? U is open, u is closed and u is open, b is closed, then I'm done, then both are open also. Now to prove that something is closed, that is equal to the closure of the u is closed means u has to be equal to the closure of itself inside y, and closure of u inside y is nothing but u closure intersection y, right? So what is my claim? So okay, let me just claim it first. So what I need to prove? I need to prove that okay, so this is my claim. So I will prove that u and b both are closed. That means both open also, right? Because the union is a full set that is given already. So so that means I need to prove that u bar intersection y equal to u and b bar intersection y equal to v. That I need to prove, right? But I already know that u bar intersection v equal to u bar intersection v equal to empty set, and u intersection b bar is empty set because they does not contain each other limit points. Okay, now with the help of that, can I show that this is the case? Yes, 1 minute. One part is obvious because u is subset of y and u is subset of u bar, so u always belongs to this set. That is obvious. Now other part you need to prove that if something is inside okay, so so one part is always obvious, right? U subset of u bar intersection y, and obviously v subset of v bar intersection y, because u bar means u union u dash, the derivative, right? So this is obvious. So now conversely, so let me prove one part. So x belongs to u bar intersection y, then I need to show that x belongs to u. So if x belongs to, this means x belongs to y, right? So x belongs to y, which is nothing but no, not if. Okay, this implies, rather I should say, this implies x belongs to y, which is nothing but u union v. So x belongs to u union v means x will be either inside u or inside v, but x cannot be inside v, that I need to prove. So if x belongs to v, then v intersection u bar not equal to 5, because x always belongs to u bar, I don't know, right? So thus x belongs to always u. So this implies u bar intersection y subset of u, and hence u equal to u bar intersection y, even y. So u is closed in y, right? Similarly v y intersection b closure equal to v, and thus uv forms a separation, right? So they are both open set and both closed set. I will just put them both closed set, and that means both open set also, because their union is the full set separation of y. Clear? So for subspace to prove separation, you can sometimes easy to find out whether one space contains unit points of other set or not, right? Okay, now let me give some example. For example, okay, so you choose x subspace of y as 1, 2, union, say 2, 3, whatever. Yeah. Now you see that. Yeah. So okay. So question is whether this is connected or not. Okay. So obviously you can think that okay, this is maybe these two are disjoint and they are non-empty, so probably they will form separation. But you think one more way, this is they cannot form separation because issue is that this is, if suppose this is U, then U contains the limit points of this V. You got 2 is the limit point of this. Okay, 2 is the limit point of this. So yeah, so what does that mean? That means this is actually U and V cannot be limit points, cannot be a separation of that, right? Okay. No, one minute. Yeah, so this contains. This is open because no. This is not even open because this is closed. Obviously, this is closed inside X, but this is not open. Because if it is if it is open set, it has to be in intersection with some open interval of R with X, right? But if you take any interval whose intersection with X, it cannot be exactly this, because any interval containing open interval containing 2, they also intersection, there will be intersection of this set also. So this is not open set. Okay, so this is not a separation, obviously. Okay, maybe if I remove these things, so say 1 and open interval 2 and open interval 2 and something, then this will be disconnected, because in this case you can choose this is U and this is V, and now you can see that neither U contains the limit points of V nor V contains the limit point of U. Okay, so this is disconnected, this one disconnected. Okay, okay, now we will give some more properties, okay, and try to prove our main results that if you have a connected space and if you know there is some map, something called continuous maps, then the image will be also connected. That is one of the major important idea. But before that, we need lots of other properties. So maybe write down proposition. Okay, whatever the proposition, I don't remember, 2, 3 or something. So suppose you have a separation and you have a connected subspace of the whole space, then there has to be one of the separation. Okay, so let U V be a separation of X and Y be a connected subspace of X. Okay, then either Y is sitting inside U or Y is sitting inside V. There is no other choice. Okay, so so how do you prove it? Now because u be a separation, then both u and v are open, right? So both u v are open in X, thus u intersection y and v intersection y are open in Y, right? And obviously the way I assume they are disjoint, so you can write down y equal to u intersection y union v intersection y, and they are disjoint, right? If they are disjoint, then what happens? So now if both non-empty, if this is non-empty, if both this is non-empty, this is non-empty, then it becomes a separation, and y becomes a disconnected subspace, right? But that is not possible. So now the connectedness of y, implies what? Implies any of at least one of these has to be not empty, right? Implies either u intersection y is empty or v intersection y is empty, right? So what does that mean? If u intersection y is empty, that means v is sitting inside, y is sitting inside v. If v intersection y is empty, that means y is sitting inside u. So what does that mean? Thus either y is sitting inside u or y is sitting inside v. Okay, this is what we are planning to prove. Okay, so what does that mean? That means whenever you have a connected subspace of a space, and if you have separation of the original space, then the connected subspace has to be inside at least, it has to be inside exactly one such open interval, not two. Okay, and from there we can define a definition that the kind of maximal connected subspace is called a component. Okay, so maximal one, that is called a component. Like for example, the 1 to 2 and then 2 to 3. Since this is a component, this is another component. Okay, so what do we learn? So whenever you have a connected subspace of a full space, and if you have separation of the full space, then the connected subspace will be sitting inside exactly one component. Like you can see that. Yeah, so the maximum one is the component. Okay, now what about if you take union of some connected subspace of a given space? Is they connected? The answer is no, always, obviously, but with certain property it will be connected. What is the property? So next proposition. So let me assume that you have some collection. So let say x alpha there be a collection of some, it can be finite, infinite, doesn't matter, collection of connected subspace of connected subspace of X, then yeah, so in this case what happened, if you have something which is connected, then it may not be connected. Okay, so I need one more property, such that the intersection x alpha is non-empty. With this help, then the union of alpha, whatever alpha may vary, may be finite, infinite, doesn't matter, is connected. Okay, so what does that mean? That means connected union of connected substrate is connected if the intersection contains at least one point. So that means there will be at least one point which is common to all those connected substrates. Okay, so then how to prove it? Again, the proof is not difficult. So you just assume that let you have a point, say x belongs to this intersection of x alpha. Okay, so this implies x belongs to x alpha for all alpha. So maybe this is my numeric set, index set alpha lambda, where alpha belongs to. Okay, and now and so what is our claim? So in this case, if we have a point, then the claim is that the new space, say y, which is union of x alpha belongs to lambda, is connected. This is my claim, right? This is our claim. Now to prove something is connected, what you need to prove? So you start with that if not, if possible not, then you have a separation, right? And then you show the contradiction. So on the contrary, let u be a separation of y. Okay, so what does that mean? That means they are disjoint non-empty subset of y such that y equal to u union v. Okay, and obviously disjoint and non-empty. Disjoint intersection is phi and they cannot be phi. Both are non-empty. Okay, but we know that the point is there, right? So there is a point x inside x alpha, and x alpha's union is y, so this belongs to y because this is union of x alpha, right? And this implies either x belongs to u or x belongs to v, right? There is no other choice because they are disjoint. It has to be one of those things, right? So if x belongs to u, then what happened? Then a alpha belongs to u as a alpha is connected, right? We just proved that connected subspace cannot lie in both component, both separation, right? If you have a separation of two open sets and a alpha is connected, it has to be one of this. We just proved it, right? And because x belongs to u alpha, so a alpha has to be this, right? And that has to be true for all alpha. What does that mean? That means this implies y, which is nothing but the union of a alpha, that is also inside u, right? And then this implies your v is empty, and this is contradiction, which is a contradiction. Yeah, so one thing you can say that how to know that this x belongs to u. I mean, it doesn't matter, x can belong to v also. In that case, you have also a contradiction, and then you will say that u is empty, right? So in any case, it doesn't matter. That is, with the law of generality, you can assume that x belongs to u. Okay, and thus this y is connected. So what does that mean? That means whenever you have something which is a union of collections, and the collection has a common point, which are all are connected, and then the whole union is also connected space. Okay, this is very important property. For example, I can give a pictorial thing. For example, so let me draw. This is one circle with one common point, like common tangent point. The tangent is same here. Okay, so this is the point x, which is common, and because all the circle is connected, so this is also connected inside R2. Okay, so another very important proposition that tells you that if you start with the connected subset of a space, then the closure is also connected. Okay, so how do I write down closure? Rather, it is more than that actually. So okay, so let me write down. Okay, not okay. This is proper corollary. As we can write down. So let me write down. Let a subset of X is connected such that not such that, and connected, and you have another subset, and B is a subset of X with B is inside this A to a closure. Okay, so that means you can add some of the limit points of A, or all the limit points of A, doesn't matter. Okay, then B is also connected. In particular, what? In particular, closure of a connected set is connected. Closure of a connected set is also connected. Is that okay? So if I prove this, then it will prove that closure is also connected, right? Okay, so how do you prove it? So you start with the separation, obviously, and then you check that something is false or not. So let U and V be a separation of B right? So you know the meaning, right? So U union V is B and U intersection V is empty, and both they cannot be empty. The both has to not empty. Okay, so this is the condition, and then A is inside B, which is A union of V is connected, that is given. Thus A is either in U or in V, because whenever you have a connected subspace, you have a separation, there has to be one of those separation, right? So with the loss of generality, we assume that it is inside U. Okay, so without loss of any generality, let A what we are assuming, what is my, yeah, A, right? So let A is actually inside U. So this implies what? This implies A bar is inside U bar, right? And this is the simple property. And if A bar equal to U bar, and this implies C. One more property, you know that your B is sitting inside A bar, which is sitting inside U bar, right? But you know that U and B are forms a separation. So that means U is also disjoint from the there is no limit points of U that contains in V, and vice versa. Okay, also you know what? Also you know that U bar intersection V is also phi, right? That property you already proved. So what does that mean? That means V is also disjoint from U bar, and this implies what? This implies B intersection V is phi. Okay, so so what does that mean? That means this implies V is himself phi, right? V was a subspace of B. Yeah, so B was a subspace of B, intersection is phi, means V itself equal to phi, and which is contradiction, right? So this is a contradiction again, which is a contradiction, and hence what happened? We have that B is connected. Okay. Okay, maybe I will stop here, and maybe we will discuss lots of other property in my next lectures. This is a new idea, so try to first digest till this. Okay. Bye.